if a particle is moving from one point to another, if a particle is in motion, then in classical mechanics, value of observable, that means this kind of measurable dynamic variable, this changes, right? This changes. Now, for every observable in classical mechanics, there is an operator in quantum mechanics. There is an operator in quantum mechanics. So, for position, there is one operator in quantum mechanics. For momentum, there is an operator in quantum mechanics. For kinetic energy, potential energy, total energy, angular momentum, each and everything which we can measure in classical mechanics, there is an operator in quantum mechanics. And who discovered that? That is basically for our calculation. For our calculation, this operator is representing the classical phenomena in quantum mechanical particle. That's why each observable or each measurable dynamic variables has an operator in quantum mechanics. Now, in the next slide, we are going to look at those observable and operator. So I will be just making one table, and you have to just write with me and just understand that what is the difference of classical versus quantum in terms of observable and operator. So first I am writing classical mechanics. Classical mechanics. In classical mechanics, the variables we call observable. In classical mechanics, the variables we call observable. In quantum mechanics, the variables we call operator. Because operator is changing functions, right? One second. Okay. Sorry. Just make table in the same way I am writing. Classical mechanics, observable. Quantum mechanics, operator. And how the operator operates on a function. In quantum mechanics, there will be operator for every classical mechanics things. For example, position, momentum, there will be some operator, and that operator will operate on some function because independently operator doesn't exist. So I will be writing the operation here. That means how it looks when the operator operates on some function. Operation is basically operator with function. Here my common function will be psi or f of x, something, anything we can write. Now, our first observable is position. Let's say our first observable is position. First, our property, our position, observable is position. And in classical mechanics, how we denote position? In Cartesian coordinate, we denote x, y, sorry. This sign is basically sign of operator, isn't it? In classical mechanics, we do not use that. Okay, x, y, z. So this is basically position. In classical mechanics, to indicate position, we just use x, y, z coordinate. In quantum mechanics, for this we just write x cap or y cap or z cap. We just use this cap. Here the operation is basically multiplication. Suppose x operates on f of x. you do not need to use a separate bracket here. It actually indicates the function is operating. Here x is operating on f of x. That means this operation is basically multiplicative operator. So we can write the operator x will be simply x and a multiplication will be with f of x. So basically x f of x, it will be the result. For example, y, similarly y operator, if it is operating on function of x, just we will write y f of x, it will be the product. This is basically the multiplication. Okay, similarly if z operates on f of x, then the result will be z f of x. Second, linear momentum. Linear momentum. Momentum means mass into velocity. So in classical mechanics, what is the formula? P equal to m into v. This is the formula of linear momentum. But in quantum mechanics, linear momentum is denoted by p cap. If linear momentum, now linear momentum can be directional. If it is in x directional, that will be px. This is the operator of linear momentum in quantum mechanics. It is basically denoted by minus I h cross. Sorry, h cross means h by 2 pi. Let's take an eraser. This only h. I h cut or h cross del x or ddx. Okay, or h cross means h by 2 pi. That means h by 2 pi, let's write h by 2 pi minus I h by 2 pi into del x. This is the same thing. Okay, now we can write this. This is the these are different forms of p of x. Okay, now we can write I h upon I square 2 pi, because I square equal to minus 1. So if this is minus 1, then you solving this entity, you can get this entity, isn't it? So h upon 2 pi I del x. So either this term or this term or this term, you can get the position, the linear momentum operator in quantum mechanics. Now you can write py operator. That means linear momentum in y direction. This is basically, this will be also simple. You just try to write in the same way. These three forms you just write without looking at the board. This is basically py. Okay, now you can write pz upon yourself. Okay, write here pz by yourself and complete it. How the operation works? Operation, if I am just taking example of px, if it operates on f of x, that is basically we have to write minus I h cross. I am just writing the first one. Mostly you will be using this. Okay, h cross del x of f of x. For example, my function is 5x. Okay, then what will be the linear momentum? What will be the value of px? So px of 5x equal to minus I h cross del x of 5x, that means 5 minus 5 I h cross. This will be the value. Okay, up to this point clear? Now we have seen linear momentum. Now 3, let's take kinetic energy. In classical mechanics we know kinetic energy is half mv square. Half mv square, we can write it m in numerator and denominator. I am just multiplying m. mv means we know p equal to mv, linear momentum, right? So m square v square means p square by 2m. So kinetic energy is basically p square by 2m. Now what will be the operator here? Now it's very simple. This is denoted by T. Total energy is kinetic energy is denoted by T. In x direction, if when there was only P, then it was like minus IH cross del x. Now if it is P square by 2m, obviously that will be px square upon 2m. That means basically 1 by 2m into px into px. This is the property of operator. It's multiplied 2 times. I means it is operated 2 times. Okay. Now px means basically 1 by 2m minus IH cross del x into minus IH cross del x. Actually, to be theoretically honest, we have to write one psi, tx psi equal to this psi equal to this psi. Then at the end we have to cancel out psi. But I am just getting into the final formula. So 1 by 2m. Now multiply minus into minus, that will be plus. I into I will be I square means minus 1. H cross means 2h cross, so 2h cross square and del 2 del x2, right? That means minus h cut square by 2m del 2 del x2. That is the operator of kinetic energy. Kinetic energy, this is the operator in quantum mechanics. For classical mechanics, the observable kinetic energy has the operator this in quantum mechanics. And how we have to use it? For example, our function psi is 3x square. Then how we will get the kinetic energy in a quantum mechanical particle? Then we have to just operate tx of psi equal to minus h cut square by 2m del 2 del x2 of 3x square. First differential it will get 6x, then it will get second differential it will get 6. So minus h cut square into 6 upon 2m 3, that is minus 3 h cut square upon m. This will be the value of total energy. Okay, now we have to just put the value. H is basically Planck constant, E equal to h nu, you know Planck equation, this h 6.626 into 10 to the power minus 34 joule second. Okay, so this is the operation we have understood. Now third thing completed. Fourth thing, potential energy. Potential energy. Potential energy in classical mechanics we call it, it is a position dependent phenomena. Position dependent phenomena. In quantum mechanics, it will also be position dependent. So it is denoted by V operator in the x direction, V y direction, V z operator z direction, and its function will also be multiplying like position. Okay. Now, if you have a little bit confusion that why it is multiplying, what does it is actually mean, we will be solving many questions, many problems of quantum mechanics. Then you will be understand that what does actually mean it is a multiplying function it has. Okay. Now last one will be total energy. Total energy means, fifth number, total energy in classical mechanics means kinetic energy plus potential energy. That means half mv square plus v. This is basically small v. Let's take it is small v. Okay. This is velocity, or this is potential energy. Okay. Now in quantum mechanics, the operator is denoted as H, total energy operator. So H is total energy operator equal to kinetic energy operator. We have written it earlier as T, plus potential energy operator, it is this. Now, if particle is in x direction, in x direction total energy will be Tx plus Vx. Tx means minus h cut square by 2m del 2 del x2 plus Vx. Similarly, we can write at y direction. Similarly, we can write total energy at z direction. Now, if the particle is moving along all direction, it will have components in all direction. That means if particle is moving all three directions, then the total energy will be h x y z. This is basically the summation of hx plus hy plus hz. This will be minus h cut square upon 2m del 2 del x2 plus v of x plus minus h cut square by 2m del 2 del y2 plus vy plus minus h cut square by 2m del 2 del z2 plus vz. Now our sorry, okay, so I am just writing here. Now if we solve it, we will be writing minus, just I am just give me 1 second, I am just creating one more slide. Okay, because this is the last part today's in this class, this is the last part. So our h cap x y z will be, if we just rearrange that equation, that will be minus h cut square upon 2m del 2 del x2 plus del 2 del y2 plus del 2 del z2 plus v of x y z equal to v of x plus v of y plus v of z. Okay, so v of x y z as total energy, total potential energy of x direction plus total potential energy at y direction, total potential energy of x direction, then overall this will be total potential energy, isn't it? Now this term in mathematics is represented as this. This is called Laplacian operator, or in short we call it Laplace. Actually this is a Laplacian operator, this term, only this entity. So the whole entity I can write as h equal to minus h cut square upon 2m Laplace square plus v of x y z, x comma y comma z. Okay, fine. So this is the operator of total energy, right? So h is basically total energy operator in quantum mechanics. In classical we say it is total energy. In quantum we will call it total energy operator, or this is the thing which we call it Hamiltonian operator. This h we will be calling it as Hamiltonian operator. So very significant equation of quantum is this, the operator of total energy. With this you can calculate the total energy of a quantum mechanical particle, right? So this is very significant. So before proceeding to the next class, you have to remember all the classical mechanical observable and their quantum mechanical operator and how they work. Okay, got it? Understood? So we are resting the class here. Meet you in the next class with a very interesting topic of angular momentum. Okay, this is basically sixth point. We have seen the five classical mechanical observable. The sixth one will be angular momentum. This will take a very long session. That's why, because in classical mechanics we have seen the linear momentum also, right? In the second, right? In point number 2 we have seen the linear momentum. Now there is another thing is called angular momentum. Okay, it is noted by L equal to R cross P. Just before proceeding to the next class, I am requesting you to just read a very basic thing about angular momentum. In classical mechanics, what do you mean by angular momentum? Okay, just read this and let's meet in the next class. Till then, have a nice day. Jai Shri Krishna. Radhe Radhe.